Go is becoming one of the most popular languages. There are good reasons why companies such as Google, Amazon, Netflix, and others use Go, and why projects such as Docker and Kubernetes are. My personal journey to Go started with two issues. One is called "The Free Lunch is Over." This article states that new CPUs have many cores, and traditional programming languages have problems working with multiple cores. The second issue is the C10K problem. In this connected architecture that is very common today, how can I serve 10,000 connections from a single process? Go solves both of these problems in a simple and an elegant way. As a bonus, it has many great features. You should have working experience with programming. I will teach you how to write code in Go, but will not discuss basic topics such as what is a function. You should also be familiar with the command line, as we are going to use it in several cases. We won't do anything fancy, but we'll use it from time to time. You should also be familiar with internet-related technologies such as HTTP requests and JSON serialization. Let's get you set up. First, you will need the Go SDK. You can either go to go.dev and download the SDK for your operating system, or you can use a package installer such as Homebrew or apt on your machine. Apart from the Go SDK, you will also need Git on your machine. Again, you can download it from the Git site or install it with the package manager. Finally, you will need an IDE, an integrated development environment. I'm going to use Visual Studio Code with the Go extension. Another popular IDE is Golang from JetBrains. Once you have Visual Studio Code installed and the Go extension, there is another step you need to do. You can either view Command Palette or Apple Shift P, and then select Go Install and Update Tools. Click on the button to select everything, and then OK. This is going to install several utilities that Visual Studio Code Go extension is using. And that's it. You're all set. Let's have a look at the Go program. Our code starts with the package main. Every Go code lives inside a package, and all the files in the same folder on the disk should be in the same package. Package main is a special package that will make your code compile to an executable and not a library. After that, we have import. Go is a simple language, and most of the functionality is inside other packages we need to import. In this case, we're importing the FMT package for formatted output. On line 7, we define main, which is a function. We use the func keyword to define the function, and then the name of the function. This function gets no parameters, and then the function body starts with the curly braces. Do not try to put the curly braces anywhere else. The Go code is automatically formatted with an external tool, and every Go code looks exactly the same. On line 8, we have a function call. We call the println from the FMT package. We always prefix the package name before the function we're calling. So FMT dot, and then we have println. Println starts with a capital T, meaning it's an exported symbol. Every symbol or function you're going to use from another package is going to start with an uppercase. We do println, and then we open parentheses for the arguments, and we have a single argument, which is a string starting and ending with double quotes, saying welcome Gophers, and we have the smiley sign. Strings in Go are UTF-8. And we have the closing parentheses for closing the arguments for the function call. And we don't have a semicolon. Most Go code will not have any semicolon in it. And finally, we have the closing curly braces for the function body. To run the code, you can go to the Run menu and do Run without debugging. If you don't see the output, click on View and Debug Console. The yellow output is from the IDE, and my output is the one in blue. Welcome, Gophers. Go comes with the Go tool. Most of the operation of the Go tool can be done from the IDE, but it's important to know how to work it in the command line, since all the automated systems, such as continuous integration, will work with the Go tool. So we can do Go run and welcome.go. This is going to compile and execute our code at one go. You can also build the executable by doing go build welcome.go. And now if we look, we see that we have a welcome executable, and I can run it and see the output. The Go tool can perform many other tasks. If you run go help, you will see some of the commands it can execute. So GoDoc can show us documentation in the command line. The env is going to print some environment variables related to Go. The FMT is the one used to format Go code. Go install and go get are used to install dependencies. Go mod is using for module maintenance. Go run is going to run the executable, and we already saw the go build to building executables. And let's not forget the go test, which is going to run the test packages for us. There are many other commands, and with time you'll probably use more of them. Let's calculate the mean or average of two numbers. So we start with package main and we import FMT to show the results. And now we define our function funcMain. We define a variable x, which is an integer, and y, which is an integer. In Go, we have several integers types. We have int and uint for signed integer and unsigned integer, and these are the integers native to the current machine. We also have integers in specific size. We have the signed ones with 8, 16, 32, or 64 bits, and the same versions but unsigned. Now we assign values to these integers, x equal 1 and y equal 2, and now we print. I'm going to use printf with %v, which is going to print any Go value, and %T, which is going to print the type. So I'm going to print the type of x, the type of y, and then calculate the mean, x plus y divided by 2, and print out the result. Now I can do run without debugging. And if you don't see the results, view and debug console. And we see that x of type int and y of type int, and the result is 1 of type int. When we divide two integers, we are going to get an integer back. So let's change this a bit. I'm going to comment out this part, and I'm going to fold this comment, and then I'm going to uncomment the other part. And this time I'm going to make x and y float 64s. In Go, we have only two kinds of floats, a 32-bit floating number and a 64-bit floating number. Let's run it again. So run without debugging. And this time we see that the type of the variables is float64, and the result is 1.5, which is expected. So this is the long variable declaration, but we are going to do something else. So let me comment this one as well. And I'm going to open the comment below. And let me fold these comments on the top. So now we can do x colon equal and not just equal. And colon equal is for defining and assigning a value to a variable at the same time. And Go is doing type inference, meaning Go will look on the value on the right side of the colon equal, defer its type, and then set the variable type to the one we want. And if you're going to run this one, we will see exactly the same result. And finally, we can go even a little bit more shorter. We can assign to two values at the same time. Let me fold this comment. So I can do in the same line x and y colon equal, and then put two values on the right side. And if I'm running this code, I'm going to see the same result. If we try to make one variable an integer and the second one a float, this is not going to work. The Go type system is very strict and will not allow you to do mathematical operations between variables in a different type. Another thing is that if you're going to declare a variable but you're not going to use it, let's say I'm going to do c equal 3, Go is going to make this a compilation error. If I try to run this without debugging, you will see that it will compile. It will tell me the variable is declared but not used. So you cannot have unused variables in Go. We have two forms of conditionals in Go. an if statement, and a switch. Let's start with an if. So here we specify x is 10, and then we ask if x is bigger than 5. Note that we don't need to put parentheses around the condition. And then we write curly braces, and then the body of the if statement. In this case, we're printing x is big. And let's run it. And we see that x is big is being printed out. We can also have if and else. So in this case, I'm saying if x is bigger than 100, we're going to print that x is very big. Otherwise, we're going to print that x is not that big. And let's run this one as well. We can use logical operators to combine conditions. In this case, we are saying if x is bigger than 5 and x is smaller than 15, we're printing that x is just right. And this is what gets printed. And we can do also OR by specifying the two vertical bars. And here we say if x is smaller than 20 or bigger than 30, we print that x is out of range. And we'll get x is out of range. Another thing we can do is an initialization statement in the if statement. So I'm having a and b as 11 and 20, and then I'm saying if fraction equal a divided by b, then a semicolon, and then the condition. And we are going to print a is more than half of b. The other form of conditionals is a switch statement. Here we set n to be 2 on line 36, and then we have switch n, the condition, and then cases, case 1, case 2, case 3, etc. And we have a default case if we don't catch any of these cases. And we're going to print 2. The last form that we're going to look at is a naked switch. So we have just a switch, and we have the conditions in the case statement. Case n is bigger than 100, bigger than 10, and again, a default clause. And when we run this, we are going to see that n is small. When it comes to looping, you have one option in Go. It is a for loop. The first one is the traditional for loop. We start with I equal to 0, and as long as I is less than 3, we execute the body of the for loop, and after each iteration, we increment I. If you're coming from Java, C, or C++, this should be pretty familiar. Let's run it. And 0, 1, and 3. We also can break a for loop in the middle. So I'm going to print a line to separate the outputs, and then do the loop as before. But now I'm saying if I is more than 1, we're going to break the loop. Let's run this one. And this one is printing only 0 and 1. The other thing we can do in a loop is continue. Continue means go to the next loop without executing the code below. So again, we're going from 0 to 3, and then if I is less than 1, we continue. Otherwise, we are going to print I. Let's run this one. And this time we see only 1 and 2. Another format of the for loop is like while in other languages. We have only the condition, and here we initialize a to 0 at the beginning, and we manually increment it inside the for loop. And again, 0, 1, and 2. The last format is like a while true or an infinite loop. So we're initializing b to 0 and checking if b is bigger than 2, we are going to break. Otherwise, we print and increment b. There is no condition on the for loop. We use a manual break to exit out of it. Let's run this one. And we get, again, 0, 1, and 2. Let's try a classic programming question. It is called FizzBuzz. And the question states that you need to print the numbers between 1 and 20, 1 per line. But if the number is divisible by 3, let's say 9, you need to print fizz instead of the number. If the number is divisible by 5, let's say 10, you need to print buzz instead of the number. If the number is divisible by both 3 and 5, let's say 15, you need to print FizzBuzz, and otherwise you just print the number. This is the statement definition, and here is a way to check if a number is divisible by other number by using the modulo. So 1 modulo 5 will bring 1, 7 modulo 5 will print out 2, this is the reminder, and 10 modulo 5 is going to be 0. Let's see my solution. So we have function main, and here we're doing a loop between I equal 1, I less than or equal to 20, I plus plus. And first we check if it's divisible by both 3 and 5, and if it's so, then we are printing FizzBuzz. Otherwise, if it's divisible by 3, we are printing fizz. Otherwise, if it's divisible by 5, we are printing buzz. And finally, we print the number. Let's run. And we see that we get the numbers. So 1, 2, instead of 3, we have fizz. Instead of 4, we have buzz, etc., etc. And in 15, which divides by both 3 and 5, we have FizzBuzz. Strings in Go starts with double quotes. Here we have the variable book assigned to a string the color of magic. And we are going to use the fmt println to print out the book. Let's run it. And we see that we have the color of magic. When we are going to print the len of the book, how many bytes are in the book, we can use the built-in len function. And we have 19 bytes in the book. We can access the first byte with the square brackets and index 0. In the fmt verb, we're going to do %v for print any Go type and %T to print the type of the variable. When we run this one, you're going to see that it is 84, which is the number for the capital B, and it's a uint 8, which in Go stands for a byte. In Go, strings are immutable. You see the IDE is painting this code in red, and if I'll try to run it, I will get a panic saying cannot assign to a book. So I'll comment this one out. To get a part of a string, you can use slice. A slice, as we specify here, from 4 up to 11, not including 11. This is known as a half-empty range. Right, and we get color. In slices, we can also skip the end or skip the beginning. So here we're saying, I want all the string from the 4th index up to the end. And here is one with no start. I'm saying I want everything up to but not including the 4th index. To concatenate strings, use the plus operator. So I'm adding T and then book from 1 to the end, going to make everything lowercase. Go strings are Unicode enabled. So I can write Unicode like this half symbol inside of the string, and this is going to work. And finally, we can use raw strings. Raw strings starts with a backtick, which means they ignore the backslash special characters like \n and \t, and you can write multi-line strings with these backticks. An even-ended number is a number whose first and last digit are the same. Your mission, should you choose to accept it, is to count how many even-ended numbers are there that are a multiplication of two 4-digit numbers. To help you out, let me show you how to convert the number to a string we have n, which is the number 42, and I'm going to use sprintf, which is like printf, but instead of printing to the screen, it returns a string. And I'm going to print the string with %q, meaning quote, it will add the quotes around the string, and the type of s. And when I run it, we'll see that s is the string 42 of type string. Here's my solution. So we start with count equals 0, and then we go for every pair of 4-digit numbers. So we do a for loop inside the for loop. We start the second for loop from A to B, so we don't count twice every combination of 4-digit numbers. Then we calculate the multiplication of A by B, and then we check if it's an even-ended number. We convert it to a string, and we check if the first and the last letters are the same. If so, we increment the counter, and finally, we print the counter. Let's run it. This is going to take a while. And finally, we have our result. A slice is a sequence of items equivalent to a list or an array in another language. Here, we have a slice of strings which contain Bugs, Duffy, and Taz. We are going to print it with the %v to print the slice and the %T to print the type. And we are also going to print the length using the built-in len. Let's run. And we see the slice, which is Bugs, Duffy, and Taz, and the type is a slice of strings, and the len is 3. Slices are indexed like everything else in Go, starting from 0. So if we are going to print loons 1, we are going to get Duffy. We can use slice notation also on slicing. This means we want everything from the first index until the end. And this is going to print Duffy and Taz. We can run the traditional for loop from I equal to 0, less than the length, and then print every loon at that location. But we have better option in Go. We have a range. So if I'm doing for I in range of loons, this is going to print the indices. So I'm going to get 0, 1, and 2. If I'm doing range, but now using two variables, the I and the name, I'm going to get the index and the value at the location of that index. So Bugs at 0, Duffy at 1, and Taz at 2. Finally, if I want only the values, I still need to do the double values on the left side. But because I'm not using I, I'm using the underscore, which is a special variable in Go, which can be undefined. And finally, I can add things to a slice by appending to it. So I'm going to call the built-in append function, loons equal append loons and Elmer, and print out the loons. And this is going to print Bugs, Duffy, Taz, and Elmer. Here is a slice of numbers called nums. I want you to print the maximal value in this slice. Here is my solution. I've commented out the printing of the numbers. We initialize max with the first number, so this is nums at 0 location. And then I'm using a slicing notation to start from the second value in the for loop. I'm using underscore and value to get just the values since I don't care about the indices. And if the current value is bigger than max, I'm assigning max to this value and finally printing out the maximal value. And when we run it, we see that we get 42. A map is a data structure where keys points to values. The keys and the values must be of the same type. So here we have a map of stocks. The keys are all strings, and the values are all float 64s. We have the Amazon, the Google, and the Microsoft stock. And we have to have the last trailing comma, the one right here. And we can use the built-in len to print out the length of the map. And this is going to print 3. When we count len, we count the number of keys. If you want to get a value, we are going to use the square brackets. So we're getting the value of the Microsoft stock. If you're looking for a stock that is not in the map or a key that is not in the map, we are going to get the 0 value for the values in the map. In this case, the values are float 64, so the 0 value is the number 0. If you want to know if a value is in the map or not, we can use two values on the left side of the colon equal. So we do value OK equals stocks of Tesla. And then if not OK, meaning the key was not found in the map, otherwise we can print the value. And we see that Tesla is not found. If you want to set a value, we use the square brackets and then an assignment. So we say stocks of Tesla is $822.12. And now we see that we also have Tesla in the stocks. We can also delete from the stocks by using the built-in delete function. So we're going to delete the Amazon stock from our portfolio. And now Amazon is gone from there. We can iterate over a map. If you're going to do a for loop with a range with a single variable to the left of the colon equal, we are going to get the keys. So this is going to print Google, Microsoft, and Tesla. If you want both the keys and the values, we can use two values on the left side of the colon equal. And now we're printing every stock and its value. Count how many times each word appears in a text. This is a very basic step in many text processing algorithms. To split text to words, use the fields function from the strings package. Also use the toLower function from the same package to convert all words to lowercase. And finally, print the map. Let's see my solution. So we import the FMT and also the strings package. Here we have the text, and I've commented out the printing of the text. First, I'm using string.fields to convert the text into a slice of strings, which are the words. Next, I'm creating an empty map from word to the count of the word. And then I'm doing a for loop on the words. I'm using two variables on the left side. The first one is the underscore because I don't care about the index. And then I'm updating the map, doing counts in the toLower of the word ++ to increment it. And finally, I'm printing out the counts. Let's run this. And we see we have A1, AND2, catch1, me2, etc., etc. Functions are the building blocks of most programming languages. Functions gives us modularity and reusability of code. You can code without functions, but it's painful. Let's define a simple function. So you define a function with the func keyword, then the function name, in this case add, and then the parameter list inside the parentheses. Here we have two parameters, a and b, both are integers. And finally, you specify the return value, which is also an integer. You use the return keyword to return the value from a function. And here in the main, we call a with 1 and 2 and val, and then print out the value. When we run it, we're going to see 3. And other things we can do in functions with Go is return more than a single value. So here we have div mode. Again, gets a and b as an integer, but this time return two integers. And when you return more than one value, you must enclose the return types in parentheses as well. Return a divided by b and a modulo b, the quotient and the remainder. Let's use it in main. So we assign two values on the left side of the colon equal, div and mode, and we call div mode of 7 and 2, and we print out the div and the mode. Let's run it. And we are going to get that 7 divided by 2 is 3, and the modulo or the remainder is 1. Here we have a function called doubleAdd. It gets a slice of integer, any location, and doubles the value at that location. Let's see it in main. So we define a slice of 1, 2, 3, and 4, and say doubleAdd the values at location 2, and we expect to see 1, 2, 6, and 4. And this is exactly what we see. Now let's try another function. This function is called double. It gets an integer and doubles the integer. And let's try it out in main. So I'm defining a value to be 10 and calling double on the value and then printing the value. And when we run this code, value did not change. Go is passing parameters by value to function, meaning it's creating a copy of the integer and passing it to the double function. A slice, like the one we're passing to doubleAdd, behaves like a pointer, meaning we create a copy of the slice, but it points to the same location in memory, so the effect is reflected outside of the function. So how can we make double work? By using pointers. In Go, we can pass pointers to values. If you're coming from C or C++, you might associate pointers with obscure code and crashes. Don't worry, the Go pointers are much safer. If you want to do all the tricks that you do in C++, you will need to use a package in Go called unsafe for a reason. So let's use double PTR. So what I'm doing is I'm passing the pointer with the ampersand to double PTR and then printing the value. And now when we run the code, we will see that the change is reflected in PTR. Go functions can return more than one value. This is used extensively in Go to return errors. A function that can err will return the last value as an error, which is a built-in type in Go. Here is our square root function. If n is a negative number, we want to return an error. So we are going to return 0 as the value, and it is customary to return the 0 value when there is an error. And then we use the fmterrorf function to create a new error. Otherwise, we're going to return the math.sqrt function and return nil, signifying no error. Let's see it in action. So we have s1 an error, which is the square root of 2. And if error does not equal nil, we print the error. Otherwise, we print the value that we got. You are going to write a lot of error does not equal nil in Go code. It might seem tedious, but I found out that my code is much more robust because Go forces me to think about errors. Let's run this code. And you see that we got the value. Now, let's try with the negative number. So we do s2, an error equal to the square root of -2, and then we check again for an error, otherwise printing the value. And this time we get an error, negative value of -2. Go also has something called a panic, which is somewhat similar to exceptions in other languages. We don't use panics in Go. Go has a garbage collector, which means you don't have to deal with memory management. When you allocate an object and stop using it, Go's garbage collector will clear it up. However, memory is just one kind of resource, and you may have many other resources in your program, for example, files, socket, virtual machines, and others. You'd like to make sure these resources are closed when you're done with them as well. Here we have two functions, one to acquire a resource, called acquire, that will return a name and a possible error, And the second one, release, which will releasing the resource. And we're just going to print out. And here we have our worker. The worker tries to acquire resource A, and if there is an error, it is going to print an error and return. Otherwise, it's going to do a defer. Defer is a deferred function call, meaning the release will get called only when the worker function exits. This idiom of acquiring a resource, checking for an error, and then deferring the release of the resource is very common in Go. And inside the worker, we're just going to print out worker. And in the main, we're just going to call the worker. Let's run this. And you see, we first have the print from the worker, and only then when the worker exits, we have the defer function. What happens if we add one more defer? So this time we're acquiring resource B, again checking for an error, and finally releasing it. When we are going to run this one, we are going to see that the worker, and then first we get the defer of B and then the defer of A. Deferred are called in reversed order. Write a function that will return the value of the content type HTTP header returned by making an HTTP GET request to a URL. So here's the function signature. It gets a URL and it returns a string and a possible error. And here is the usage of the function in main. We call the function, we get the content type and a possible error. If there is an error, we print it. Otherwise, we print the content type. Have a look at the net HTTP package on how to make an HTTP request and how to inspect the headers. Here is my solution. We import the net HTTP package, and then we go over the content type function. First, we make an HTTP GET request, which returns a response and a possible error. If there is an error, we return the empty string, which is the zero value for a string, and the error. Then we defer closing of the response body. Make sure to close the body. Then we get the content type from the response header. If the content type is empty, we again return an error that we couldn't find it. And finally, if everything is okay, we return the content type and nil. In the main, we are calling the function as before. Let's run it. And we see that LinkedIn is returning HTML encoded as UTF-8. You can do a lot with the built-in types in Go, but there are times you'd like to define your own data structures. In Go, you will use a struct to combine several fields into a data type. Let's assume you're keeping track on a campaign budget. So here we have our budget. We say type, budget, struct, and then we list the fields and their type. Here we have campaign ID, the balance, which is float 64, and the expiration time. And now we have our budget. So B1 is the budget, the campaign is kittens, the balance is $22.3 US, and the expiration time is 7 days from now. And we are going to print out the budget. So, bringing up the command palette and start without debugging. And we see the budget is printed out with curly braces, kittens, the budget, and then the date. If you want to print more details on a budget, you can use the %#v. Once you do that, and let's run this one again, you're going to see the type, then the curly braces, and then the field name followed by the value in quoted format. If you want to access a single field from the budget, you can use the dot notation. The dot notation works both for structs and for pointers to struct. You can also create structs by specifying fields by name and not by position. Here we specify that the balance is $19.03 and the campaign ID is puppies. And notice that the expiration date is omitted. This is fine. When we're going to print it out, you're going to see that we get the campaign ID is puppies, the balance is 19.3, and the expiration time is the zero value for that field type. In our case, the expires type is time, and the zero value for time is January 1st, the year 1. Finally, we can define the whole budget with the default values. So we define variable 3 as a budget, and we're going to print it out. And now all of the fields are going to be the zero value for their type. So the campaign ID is the empty string, the balance is 0, which is the zero value for floats, and again, the zero value for time. If you're coming from languages such as Java or C++, you might wonder if you can have private or protected fields which are not exposed outside of your package. In Go, this is very simple. Everything that starts with an uppercase is accessible from outside the package. Otherwise, it's accessible only from within the current package. In Go, we call these exported and unexported symbols. Structs are nice for organizing data, but they have more power. You can define methods on structs. So here is our budget, and now we define a method. Unlike a regular function, this function gets a receiver. B is called the receiver of type budget, and then the method name timeLeft without any arguments, which returns a time.duration. And we take the expiration time and subtract the current time in UTC. And now we can use this method in our code. We create a budget that expires in 7 days, and we are going to print out how much time is left. So start without debugging, and we are going to see we have about 167 hours to go. Let's add another method. This method is called update. And this method is going to change the balance inside the budget. Because it's going to change the balance inside the budget, we are going to pass a pointer of budget. This is known as a pointer receiver. Every time you change the struct, you are going to pass a pointer receiver. And let's see an example. We are going to update, add $10.50 to the budget, and print out the new balance. And we got $32.8. If you're coming from object-oriented languages such as Python, Java, C++, and others, you are used to have a constructor or an initializer method that is called when an object is created. In Go, we write a function, usually starting with a new, that returns a new object with a possible error value. Let's see an example. So here we have our budget with the campaign ID, balance, and expires. And now we create a new budget that gets the campaign ID, balance, and expiration time as arguments and returns a pointer to a budget and an error. And here we can do data validation. So we make sure that the campaign ID is not empty, the balance is not negative, and the expiration time is in the future. And now we create our budget object from the parameter passed to the function, and finally return a pointer to this budget and nil, signifying there was no error. If you're coming from C or C++, you might cringe at returning a pointer from an object allocated inside the function. Don't worry, the Go compiler does an escape analysis and will know to allocate the budget on the heap. And now we're going to use this new budget. So we create the expiration time and we create a new budget for puppies with a budget. And if there is an error, we're going to print it out. Otherwise, we're going to print the newly created budget. Let's run it. And we see that we got a budget with the values we've sent. Let's try one with an error. So I'm going to create a new budget for kittens, and the balance itself is going to be negative. Let's run this one again. So the first budget succeeds, but the second one says balance must be bigger than 0. Define a square structure. It should have 3 fields, x and a y, which are integers, and a length, which is also an integer. create a new function to create a new square, and add two methods. One, move, which will move the square by delta x and delta y, and an area that will return the area of the square. In the main, you should be able to create a new square with new square, move it to a new location. You can print it out and also print out the area. Here is my solution. Initially, we defined the square type to be a struct with three fields, x, y, and length. Next, we're going to define the new function. It gets parameters for each field, so x, y, and length, and returns a pointer to a square and a possible error. First, we check for errors. In this case, if the length is smaller or equal to 0, we return an error. Then we create a square from the parameters and return a pointer to the square and nil, signifying no error. Now the move method. So the move method gets delta x and delta y and a pointer to a square as a pointer receiver and adds delta x to x and delta y to y. The area, which does not change the square, can get a non-pointer receiver to a square and return the length times the length. And finally, we can combine all of these together. So we use the new function to create a square. If there is an error, we use the log.fatalf, which is going to exit the program with a non-zero value. And if there's no error, we're going to move the square, print it, and finally print out the area. So debug and start without debugging. And we're going to see that our square is at 3 and 4, started at 1 and 1, and we added 2 and 3, and the length is 10, and the area is 10 multiplied by 10, which is 100. Say we have a square structure, which has a length, and also a method called area that returns the area of the square. We also have a circle with a radius, and also an area, which returns the area of the circle. And now we want to calculate the sum of several shapes. So we are going to do sum areas which get a slice of shapes, and we'll see what a shape is in a second. We start by total equals 0, and then for every shape we add the shape area to the total, and finally return the total. So what is this shape? Shape is an interface. An interface defines a set of methods that a type should implement. In our case, the shape interface has a single method, an area, which takes no arguments and returns a float 64. And both the circle and the square has this method. So we can create a square and calculate its area. We can create a circle and calculate its area as well. And we can create a slice of shapes from this square and circle and calculate the sum of all of these shapes. Let's run this. So debug, start without debugging. And we see we get the area of the square, the area of the circle, and the sum of these areas. Interfaces are very useful abstractions, and you'll see them a lot. For example, the IO reader interface defines something you can read from, and there's the equivalent IO writer which you can write into. Using the IO reader interface, you can use the same code to work with files, sockets, compressed files, and even digital signatures. In this challenge, you are going to implement the IO writer interface, which has a one method of write, which has a single method called write that gets a slice of bytes and returns how many bytes were written and if there was an error. Here we have our capper, which is turning everything into uppercase. If you're going to wrap capper over the standard output and then print into the capper, we should see hello there printed all caps to the standard output. Here is my solution. Here is the capper struct. It is going to have only a single field WTR, which is the underlying IO writer. And then, in order to implement the IO writer interface, we implement the write method, which gets a slice of bytes and return an integer for how many bytes are written and a possible error. First, we calculate the diff between the lowercase a, which has a higher value, and the uppercase a. Second, we are going to create a new byte slice. We don't want to change p. Then we iterate over every byte inside p, and if it's between lowercase a and lowercase z, we reduce the diff to make it an uppercase letter and assign it to the output. And finally, we return the result of calling the underlying IO writer write method. And now we can use copper over stdout and print out hello there. So debug, start without debugging. And we're going to see hello there all in uppercase. During the recording of this course, Go 118 came out. One of the biggest changes that comes with Go 118 is generics. Let's see what it means. In generics, an interface can also be a set of types. So I'm saying that the ordered interface is either an integer, a float64, or a string. And now I can use this type in my function. So I'm writing a minimum function, which has a type t, which is a generic type, with the constraint that it is ordered. And from here, we continue as usual. We're saying that minimum gets a slice of t and return a t, a single value, and a possible error. First, we check if the length of value is 0, we need to return the 0 value for t and an error. So we define a variable 0t and then return it and an error saying minimum of an empty slice. If there are values, we start with the initial values, then do a for loop, compare, and assign to the minimum value. And finally, return the minimum value and nil signifying an error. And now in main, we can use min both on a float64 slice and on a string slice. So open the command palette and start without debugging. And we see that the minimum of the floats is 1 and the minimum of the strings is a. Go's error handling is pretty simple. You treat errors as values and return them. But sometimes we want more, like stack traces, which help us diagnose errors. Dave Cheney wrote a wonderful package called pkg errors, which adds stack traces and other things to errors. This package influenced the changes in Go 113 to how errors are handled and the new functions in the built-in errors package. Let's have a look. First, we import pkg errors, and this is a drop-in replacement to the built-in errors pkg. Say you have a configuration struct that you want to read from a file, and you have the read config that gets a path and return a configuration and a possible error. And here we do the idiom of opening a resource, in this case a file, checking for an error, and right away deferring closing of the resource. In the error handling, we use errors.wrap. This is coming from the pkg errors, and we are wrapping the current error that came back from OS open with our own message. And if there's no error, we create a configuration and return it. This is a function to set up logging, and we open a file for append mode. If there is an error, we just ignore it. Logging will go to standard error. Otherwise, we set the output of the logging package to this file. And now in the main, we first set up logging and then try to read this configuration file. This is going to fail because I don't have this file on my machine. In the case of an error, we are going to print to standard error the error that we got back with the %s verb, which is just going to print the error. And then we're going to use the %+v when printing it with the logging package, which is going to print also the stack traces. And finally, we're going to exit the program with a non-zero value. Otherwise, we're just going to print the configuration, but we won't get here. So let's run it. Start without debugging. And we see that we get can't open configuration file path to config.toml, no such file or directory. And here you can see now that a new file was created, app.log, and in this file we have the error message, but we also have the full stack trace of where we got to the error. The usual method in Go for signaling errors is to return an error value. However, there are cases when there's an error you can't handle and you'd like to signal this. In Go, there's a built-in panic function that will do just that. Let's have a look. So here I'm defining vals, which is a slice of 3 values. And now I'm going to access vals at location 10. And I'm going to add a println just to make the compiler happy. Let's start without debugging. And you see that I'm going to get a panic runtime error, index out of range. You can create panics by yourself by calling the panic function. But this is not considered idiomatic Go. And as we say in the Go proverbs, don't panic. Let me comment that out again. Let's say that I do want to guard against something that might panic. I can write a function like saveValue. SaveValue gets vals, a slice, and an index, and it's going to return an integer and a possible error. And the way we guard against panic is inside the defer. Inside the defer, we call in the built-in recover, which returns something. If this something is nil, there was no panic. Otherwise, there is a panic. And we need to convert this value into error. So I'm going to use fmt errorf. And what is this error in line 28? Here I'm using named return values. You see n is an integer and error is an arrow. These values, the named return values, are like local variables inside the function. So when I'm assigning error here, without the colon equal, just with an equal, I'm assigning to this error, which is the return value from the function. And finally, in the function body, I'm just trying to return the value at the certain index and nil signaling there is no error. Now let's use it in our function. So I'm going to say v and error equals saveValue. If there is an error, I'm going to print it. And finally, I'm going to print out the value of v. You can see that there is no panic. I'm printing the error, and v has the 0 value for integer, which is 0. Services or servers usually store their process ID in a file. When you want to terminate the service, you need to read this process ID from the file and then terminate the service. You need to write a function called killServer. It should read the process ID from the file, convert it from a string to an integer, and finally print out killing the server with process ID. You need to think about error handling and what to do in each case of an error. And then in the main function, you are going to call the kill server with server.pid, and if there is an error, print out the error to standard error. Here is my solution. The function killServer. We first try to open the file. If there is an error, we return the error as is from the open. Otherwise, we defer closing of the file. Then we have the PID variable, and we're using fscanf to try and read from the file into this integer. If there is an error, we use errors.wrap to wrap the error with the bad process ID. And finally, we are going to print out that we're killing the server. After killing the server, we are going to remove the file. In this case, we are going just to log the error, but not return it, because this is not an error if you can't remove the file. And finally, we return nil, signaling there is no error. And the main stayed as is. So let's run the code. Start without debugging. And we are going to say there's open server.pid, no such file or directory. So let me add this file. So I'm going to create server.pid, and I'm going to write 7 in it and save. And now I'm going to run again the code. This time I'm going to see bad process ID expected integer. So let's go to server.pid, and instead of 7, we'll write a valid number. And let's run the code again. This time when we run the code, we see killing server with PID equal 7, and the server.pid is gone because we removed it. Go's concurrency units are called Go routines. They are very light, and unlike processes or threads, you can spin several thousand of them on a single machine. Let's see an example. Let's say I have this function called return type. It gets a URL, tries to do a GET request to the URL. If there is an error, it's going to print out the error. Otherwise, it's going to defer closing of the response body, get the content type HTTP header from the response, and print it out. And here we have the serial function. It goes one URL at a time and try it out. In the main, we have a list of URLs, and we measure the time by calling time.now, calling the serial method, and then printing out the time. Let's run it. So start without debugging. And we see that we get from Go text HTML, and from GitHub an HTTP bin application JSON, and it took us 2.6 seconds. And now let's write a concurrent version of this function. So I'm going to start a Go routine per URL, but I need to know when these Go routines are done. So I'm going to use a wait group from the sync package. Wait group works by adding one for every Go routine, and Go routines are signaling they are done by calling wg.done. Finally, we're going to wait for all of the Go routines. And then for every URL, I'm incrementing the counter and then creating a function and using the Go keyword, run it in a separate Go routine. It is going to call the return type and then signal that the function is done. And now let's measure this version as well in our main. So start without debugging. First the serial one and then the concurrent one. So we see that the serial one took 2.15 seconds and the concurrent one about 0.4 of a second, about 5 times faster. The preferred way to communicate between Go routines is by using channels. You can think of a channel as a one-directional pipe which has a specific type, such as an int or a string. The two main operations that we do on channels are either sending a value to a channel or receiving a value from a channel. Both of these operations are going to block if there's nobody on the other side, meaning if you're going to send and there's no receiving Go routine, you're going to get blocked. And the same in the other direction. If you're going to receive and there's no sending Go routine, you are going to get blocked. Let's see an example. So here, I'm creating a channel of integers and sending a value into the channel. And then here, I'm getting the value from the channel, assigning it to val, and printing out the value. When I'm going to run this code, it is going to panic. With all Go routines are asleep, a deadlock. When I'm doing a send operation, we are blocked until somebody is going to read from the channel. But there's nobody reading because we're still blocked here, and Go has a mechanism to detect deadlocks and panic. So to fix this, I'm going to send the value in a Go routine. So I'm going to start a Go routine that will send the value to the channel, and this go routine will run concurrently to the main one, which will receive from the channel and print it out. And when we run the code, it is going to print 353. Here we're going to send several values to the channel. So count is 3, and in a go routine, we're going to count up to count, and every time send this value to the go routine. And in the main, we're going to run also up to count, receiving value from the channel and printing them out. And we run this one, we're going to see that we're sending 0 and receiving 0. Sending 1, receiving 1, sending 2, and receiving 2. Every time, this go routine is blocked until the main is reading from it. And main is blocked until this go routine is sending. Another thing we can do to go routine is to close them. This is signaling that there are no more values in the channel. This allows us to do a range for loop over the channel. So I'm generating a go routine 3 times, I'm sending a value, and finally I'm closing the channel. And here, now I can do for I in range of channel, print out receiving. Let's run this one. And we see that we're sending 0, received 0, sending 1, sending 2. And finally, there is another type of channels, which are buffered channel. Let me fix this error. This is value 2. So here we create a channel 2, which is a buffered channel. This channel has a buffer of 1, meaning this means that I can send one value without blocking. The second value sending in is going to block. So when I'm sending 19 now, this is not going to block like it did at the beginning. And now I can read the value and print it out. And here we see all the printouts. And finally, 19 without a panic. In the GoRoutines video, we waited for the GoRoutines using a sync.wait group. Changed that to use a channel. So here's our return type function that prints out the content type. And here in the main, we are spinning several GoRoutines, and now we need to wait for them. Here is my solution. The return type function now gets an output channel where it returns the error. We are getting the URL. If there is an error, we send the error over the channel. Otherwise, we get the content type and then we send the content type over the channel. And here in the main, we get the URLs, we create the response channel, and then for every URL, we send a GoRoutine with return type and the channel to return the result. And now we run a for range as the number of URLs we have. We get the output value from the channel and printing out. Line 35 is going to block until we get a value in the channel, meaning we will wait for a GoRoutine to finish. Let's run it. So start without debugging. And you see that I'm getting all the values from the GoRoutines. The built-in select let us work with several channels at the same time. Let's have a look. So here I'm creating 2 channels, channel 1 and channel 2. I'm creating a function that is sending a value to channel 1. And then I'm using select for case we got a value from channel 1 and case we got a value from channel 2. What select is going to do is once one of these channels becomes available, and this is true both for receiving and sending, it is going to enter the specific case. So if we're going to run this code, we're going to see that we got 42 from channel 1. One thing that select is used for is timeouts. So we create a channel of float 64, and then we create a function that is going to sleep 100 milliseconds and send the value of pi to the channel. And now we are going to say, if we get the value from the channel, meaning the go routine finished in time, we are going to print out the value. Otherwise, we're going to print out timeout. When we're going to run this code, we are going to see that we got a timeout because time.after got 20 milliseconds, where the go routine has slept for 100. So let's add a 0 to the time.after and run it again. This time we see that we see the printout from this case. Behind the scenes, the time.after is spinning another go routine that is going to sleep for the given duration and then send the value over a channel. The context package is a built-in package which is used for deadlines and cancellations. It even has an accompanying blog post by the Go team. Let's see an example. Assuming that you're running a real-time bidding. Let's have a look at the code. So we have a bid for an ad. There is the ad URL and the price of the bid. And then your algorithm team wrote some code. We simulate the algorithm runtime by sleeping for 20 milliseconds and then returning a bid for Azaras at 19 with the price of 5 cents. However, there is a time limit on bids. So if the algorithm does not finish in the allocated time, you are going to return the default bid, which is the URL for the default bid and a price of 2 cents. So here is our function. It gets a context as the first value and then the URL. It is going to create a buffered channel to avoid a go routine leak, and then spin a go routine that will call the algorithm on the URL and return it on the channel. And now we're going to use select. In the case we got the bid from the channel, it means that the algorithm finished in the allocated time and we can return it. If the select goes to the context.done method, which returns also a channel, this means the algorithm did not finish in time and we are going to return the default bid. Let's see how we can use that. So every time we create a context, we create it from another context. There is the primary context.background, which is the parent of all contexts. So we do a context with timeout, starting from the background, and give it a timeout of 100 milliseconds, which is enough time for the algorithm. We defer the cancel, give the URL, and then call our function and print out what we got. In the second case, we're going to create a context with not enough time, only 10 milliseconds. Again, defer the cancellation of the context, give it the URL, and print out the bid. Let's run it. Debug, start without debugging. And you can see that in the first case, we got the ad that is 5 cents from the algorithm. And in the second case, when we didn't have enough time, we get the default bid with only 2 cents. I want you to calculate the total download size for a given month concurrently. For each month, we have 2 files, green and yellow. For example, this is the one for March 2020, green and then yellow. What you are going to do is you are going to issue an HTTP head request, which here I'm doing using the CRL command line client with a -i. And the head request is going to return the size of the file in the header without returning the whole file. The current code has a serial algorithm that does that. We have the URL template and the colors, and a function to get the download size from the URL. It creates a new request, then do a head request on this request, checks the status code, and finally convert the content length header to a number. And in the main, we start the time, initialize the size to 0, and then for every month and for every color, we create a URL for that month and that color, print it out, get a download size. If there is an error, we exit the program, otherwise add it to the total size, and finally calculate the duration and print out the size and the duration. Let's run it. Let's open the debug console, and we see all the printouts for every month. And finally, we see this algorithm took about 5 seconds to run. You need to turn this algorithm to concurrent one by using a Go routine per URL. Here is my solution. The download size function did not change. What I did change is add a function called sizeWorker. This one is going to get a URL and a channel to return the result. It is going to print the URL, create the result, set the size and the error, and send over the result over the channel. The result is a struct. When we work in parallel algorithms, we need to return as much context as we can. So returning the URL, the size, and if there was an error. And now in the main, we are going to split the algorithm into 2 parts. The first part is creating the channel and then spinning Go routines. For every month, for every color, we create a URL and then we call the sizeWorker in a separate Go routine. The second part is collecting the results. So we know how many Go routines we had. It's the number of colors times 12. And then we do a receive from the channel, check for an error, and if there's no error, we add to the size. Finally, we calculate the duration and print out the size and the duration. Let's run this one. And here we finished in 1.3 seconds, much faster than the serial algorithm. Go comes with a rich standard library, and it's getting better every new release. However, in some cases, you'd like to use packages that are not in the standard library. Before you start using third-party packages, I encourage you to read this wonderful post by Russ Cox from the Go team. I'm not saying not to use third-party packages, but do so while factoring in the risks. The standard way to manage dependencies is with Go modules. Every project has a go.mod file. The go.mod file is at the top of your project. Here's the go.mod for the exercise file. It is the top directory when you clone it from Git. This go.mod defines the module, define the minimal Go version, and define the set of requirements that we have. We have 2 sets of requirements here. These are called the direct requirements, the one that we use in the code. These are the indirect requirements, and these ones are the dependencies of our dependencies. In the rare case that you're starting a project from scratch, you will need to create go.mod by yourself. You can do it from your IDE. So we have go initialize go.mod, and we need to give it the module name. Or we can start from the command line go mod init and then the name. So let's say github.com, 53 solutions, Go essential. Once we have a go.mod, we can add dependencies. We can do it in 2 ways. We can either do go get to get a dependency, or we can write the imports in our code and then run the go mod tidy command, either from the IDE or again from the command line. I highly recommend that you read the documentation to see what they can do. But in the day-to-day case, go mod tidy is your best friend. Go comes with a built-in testing framework. I won't try to convince you that testing is important, and it is. I'll show you how to use the testing framework. As everything in Go, the testing suite is simple, but will cover everything that you need. Here we have our code that computes the square root using Newton's square root method, and we would like to test it. Because we're dealing with floating points, I wrote a small utility function to check that 2 values are almost equal. And here is our test. You define a test with a function that starts with a capital T and accepts a single argument, which is a pointer to a testing.t structure. The Go tool will scan files that end with _test.go, and inside of them will run all the function that matches that signature. The Go build tool will ignore all files that end with _test.go. So what do we do in our test? We call the square root function. We check if there is an error, and if there is, we are going to use fatal F that is going to stop the execution of the test right here. There is also an error F that will mark the test as failing but continue running. After that, we're going to check that the value that we got is almost equal to the expected value that we want. And if it's not, again, we're going to call fatal F with a T. And now we can run it. We can run the test from inside the IDE, either by run test or debug test if you want to place a breakpoint. So here I'll click on run test, and I'm seeing that the test is failing. Or you can run it from the terminal. And this is what will happen when you run things from continuous integration system such as GitHub Actions or Jenkins. So I can do go test, and it's going to run the tests in this location. I can add a -v to show the names of the tests being run. Sometimes we'd like to run a test on more than a single input. In Go, we call these table-driven tests. Let's see an example. So I'm defining a test case, which is a struct, has a value and the expected value. And then I'm defining the test cases. So for 0, I'm expecting 0, for 2, I'm expecting 1.4, and for 9, I'm expecting 3. And now I'm running for every test case. I'm going to run a subtest by calling t.run. I'm using fmt.sprintf to generate the test name, and then provide a function which again gets a t. And this function calls sqrt, checks for an error, and also check that the value that we got is almost equal to the expected value. And again, here we can run it through the IDE, or we can run it from the command line. And when you see that with the -v, we see that the name of every subtest is printing out. If you have sub-packages, make sure to run go test with /.. to run recursively the tests in every sub-package. The Go testing library will cover all your needs, but it's a bit verbose to write tests. The Testify package contains several packages that help out with writing tests by making it shorter to write them and providing a lot of utility function. It has several sub-packages. Assert adds all kinds of assertions, and it works like t.error, meaning it is going to mark the test as failing but continue running the test. Require has the same set of functions as assert, but instead will work like the t.fatal, meaning it will mark the test as failing and stop the test execution. And this is the one I use most. Apart from that, there is also a sub-package for mocking and a suite which is like a traditional test struct. Let's see an example. So here is our test simple from before. We had to write the almost equal so we can compare two floating point numbers, and we wrote a t.simple with two ifs. Once we start using Testify, so we import Testify require, and then we call the value and the error, and then we use the utilities from Testify. Require no error gets the t from the current test and the error. If there is no error, it will do nothing. Otherwise, it will mark the test as failing and stop the execution. And in Delta is very much like our almost equal. We give it again the test, the number that we're expecting, the number that we got, and the allowed difference. And once we run this test, it is going to pass as well. In our test many functions, we wrote the test case manually in the code. I'd like you to change it, and instead of writing the test cases in the Go code, read them from a CSV file. This has the advantage that people who do not know Go, such as product managers, can add test cases. So your code should have test many and then read the test cases and check them. To work with CSV files, you can use the encoding CSV package from the standard library. Let's check out my solution. So I'm going to use encoding CSV to read from the CSV. And I'm going to use the strconf package to convert the textual values in the CSV into floating point values. And finally, using Testify require to make writing the test shorter. And here is the test case that we defined as a struct. And now I'm writing a utility function to load the test cases from the file. Utility functions in testing usually get the current test. So instead of returning an error, they can use require or fatal F to signal there was an error. So load test cases gets the current test and returns a slice of these test cases. We try to open the file, check there no error, and defer closing of the file. Now we create an empty slice of test cases and a CSV reader to read from the file. We iterate with a for loop, get a record, check if it is the end of the file, we break from the for loop. Otherwise, we check we don't have any other error. And now we convert the first field to the value and the second field to the expected. Finally, we create a test case and append it to the current cases. Once we're done, we return all the cases back. And now our test function is very short. We do a range on the slice being returned from load SQRT cases, create a subtest, call SQRT, check for no error, and check for a valid value. And now we run the test and it passes. One of the advantages of using Go that is a very fast language. But in some cases, the code is not fast enough. And then you'd like to measure how fast the code is running, and also to find out where are the bottlenecks or where your code is spending your time. Go provides solution for both of these with the benchmarking and profiling that is built in with the Go tool. Let's have a look. Say we have a function called tokenize that will return a list of tokens found inside the text. We would like to see how fast it's running and where does it spend its time. Before you start, you will need to install GraphViz, which has the dot utility. You can either install it from the GraphViz site or via your package manager. So, we write a benchmark. The benchmark is written in a test file that ends with _test.go. We have our bench text that should be similar to average sentences that you are tokenizing. And now we run a benchmark. So benchmark starts with the word benchmark and after the name of the benchmark, and it gets a testing.b instead of testing.p like a test function. And we run from 1 to b.n. We call our function, and we can also do some validation that the code is working nicely. And we can run the benchmark from inside the IDE. And we can see that it's about 7,000 nanoseconds per operations. We can also run it from the command line. So we can do go test, and we need to tell it to run the benchmarks, so bench everything. And we can also say that we're not interested in running the tests for now, just when we're checking. And when it's going to do that, we are going to see again that we are around 7,000 nanoseconds per operation. When it comes to profiling, we can also tell the benchmark that we want CPU profile equal CPU.prof. And this is going to save the profiling information in a file called cpu.prof. To view this file, you can use the pprof tool. So go tool pprof, and I'm going to use the HTTP to see it on the browser, and then cpu.prof. And this is going to give us a nice view of where our code is spending its time. This is the critical path, and we have some other calls to other functions. There are several other views, such as top view, which is pretty much textual view. We have a flame graph as well. And we can take a peek or a source. Depending on your preferences, pick which one you like. I usually start with the top. When you're working in distributed environment, usually over the network, you will need to serialize messages and send them as sequence of bytes. There are many serialization formats, such as JSON, message pack, protocol buffers, XML, and many more. JSON is a good default since it's widely used and natively understood by the browser. Let's look at an example. The encoding JSON package will cover your needs when it comes to JSON serialization. You can either use marshal and unmarshal to work with byte slices, or decoder and encoder to work with IO reader and IO writer. Let's see an example. So here we import encoding JSON, and here we define the method that we're expecting. So we have a request, which is a structure. We have a login, a type, and an amount. And we are using these field tags on the right side to say which fields from the JSON correspond to which fields inside this struct. And here we have an example data. This is a JSON message that contains these fields. And now, here is our main. We create a strings.reader to simulate an IO reader, which can be a socket or an HTTP request. And then we create a JSON decoder on top of this reader. Next, we define our struct, and we call the decoder.decode on a pointer to our struct. If there is an error, we exit with an error message. Otherwise, we are going to print out what we got. So let's start with our debugging. And let's see the console window. So we see that we got the Scrooge McDuck is the login, the type is a deposit, and the amount is $123.4. When we want to work on the other side of things, we need to use a JSON.encoder. So I'm going to create a response. Assuming the previous balance is $1 million, the response, and this time I'm using a map from string to interface. I can also use a struct. And I'm saying OK is true, and the new balance. And now I'm using a JSON encoder on top of the OS standard output and checking if there was an error while encoding. Let's run this one. And now we see what we got, and also the output message. The balance is now $1,123.40, and OK is true. A common way of communicating between processes is calling APIs. One of the most common API is called the REST API. It is JSON as serialization over HTTP. The net.htp package will cover all of your needs. It contains both an HTTP client and, as we'll see later, also an HTTP server. So let's have a look. First, we're going to make a GET request. So I'm using the net.htp package, and then I'm getting a response by calling http get on httpbean.org/get. httpbean.org is a site for testing your HTTP client. I'm checking if there is an error. If not, I'm deferring closing of the response body, and I'm going to copy to the standard output whatever came from the response. Let's run it. And we see that HTTP bean send us the arguments, the headers, etc., etc. If you want to make an HTTP post request, we can use the post method. And this time we're going to combine it with some JSON data. So here I have a job. We have the user, the action, and the count. And now I'm going to create such a job with the user Saitama. The action is a punch, and Saitama always needs just a single punch. And now I'm going to create a byte slot buffer, which is an in-memory reader and writer. I'm going to use the encoder to encode the data into the buffer. And now I'm going to call HTTP post. I'm giving the post three parameters: the URL, the content type, which is JSON, and a body, which is an IO reader, in this case, our in-memory buffer. And finally, again, we're going to copy whatever HTTP bin send us back. So let's run this one. And here's the first one, and here's the second one. So this is the data we sent and the headers that were sent to HTTP bin. The fallacies of distributed computer states that the network is not reliable, the latency is not zero, the network is not secure. Wherever you work with external services, you need to guard yourself. And in this case, we're going to talk about two things you can help yourself: setting a timeout and limit the amount of data that you read. With the use of the IO package, the NetHTTP package, combined with the context package, you can achieve that. So to start, we'll create a context. This context has a time limit of 3000 milliseconds, or 3 seconds. And then we create a new request with context, given our context, a get method, the URL, and nil for a body. And now we do HTTP default client.do with the request. When we start reading the data, we can define how much data we want to read. In this case, I'm going to define a single megabyte, and then I'm wrapping the response body with IO limit reader, which is going to limit how much we read. And then I can work with the result. In this case, I'm just going to copy it over to the standard output. So let's run the code. In this case, we see that we get back my IP. Let's change the timeout. So I'm going to change the timeout to 3 milliseconds, and then I'm going to run the code. And this time you see that I'm getting an error, context deadline exceeded. On the other side, I can also limit how much bytes am I reading. So let's say just 10 bytes. And then when I'm going to run this code, the HTTP request will succeed, but I'm going to get only part of the data. GitHub provides an API that you can query. For example, if you're going to call the https api.github.com/users Tebeka, which is my user, we're going to get back a JSON document. This JSON document contains, among other things, my name, the name of the user, and the number of public repositories that I have, which is 84. I should trim that down. So you should write a function called userinfo that gets a login and returns the user struct. This user struct should contain the login, the name from the name field, and the num repos from the public repos in the JSON. To test in the main function, we have a call to userinfo for my user. Let's check out my solution. First thing I'm doing is letting the JSON package know that the num repos fields in the user struct comes from the public underscore repos in the JSON document. And next, I have the user info. First, I'm constructing the URL using sprintf and url.pathEscape to make sure that I get a valid URF. Then I'm making an HTTP request and checking for an error. If there is no error, I'm making sure that I close the response body. I'm also checking the response status code to make sure that I got a good status code. Otherwise, I return an error with the status, not the status code, from the response. After that, I'm decoding the JSON. So I'm creating a user pre-populated with the login using a JSON decoder to decode. And if there is an error, I'm returning this error. Finally, I'm returning a pointer to the user and nil signifying no error. And the main did not change. Let's run it. And you see that I got the user, my login, the name, and the number of public repositories. The NetHTTP package also contains a production-ready, fast, secure HTTP server. Let's see how to work with it. When working with the HTTP server, you define handlers. These are functions that get two values, W, which represents the response where you write to, and a request, which represents the incoming request. This handler is the health handler, returns only OK to the client. For the second handler, we are going to define both the request and the response structures. So we are going to get a math operation with an operator, left and right operands, and a response that contains an error and a result. When we work with handlers, we usually follow 3 steps. The first one is decode and validate. So I'm deferring the closing of the request body, creating a new encoder, creating a math request, and then using decode to decode the JSON. And after I decoded the JSON, I also validate that the data is okay. In this case, I'm checking that this is a known operator. The second step is doing the work. In this case, I'm creating a math response, and then depending on the operator, I'm doing the calculation. And finally, in the last step, I'm encoding the result. I'm setting the header type to application JSON. And then, if there is an error, I'm setting the status to be bad request. And finally, using JSON new encoder, I'm encoding. And if there is an error, I'm logging out the error. In the main package, I'm routing the endpoints for my server. So /health will go to health handler, and /math will go to math handler, setting the address and then telling the server to listen and serve on that address. This is a plain HTTP server. You can also use HTTP listen and serve TLS to serve over TLS or HTTPS. Let's run the code. And we have that the server is ready. So I'm going to the terminal. I'm going to use the command line curl, but you can also use visual tools such as Postman or Insomnia. So curl HTTP localhost 8080 and then health. And I'm getting OK. And now I can do curl-d for data. And now I can send that the op that I want is minus. The left-hand side is going to be 1, and the right-hand side is going to be 6.2. To HTTP localhost 8080/math. And I'm getting an empty error and the result of -5.2. In this exercise, you need to implement a server for a key value database. Here we have our server struct, which contains a DB, which is a database that has a get and a set methods. I already written the DB for you, so you don't need to write it. And you have the database handler, where you need to write the work. And finally, you need to do routing and start the server. The API should be, if I'm doing curl/d to the server, it is going to set the key. Otherwise, if I'm doing just getting, I'm going to get the key. And if I'm going to a key that does not exist, it should return not found. Limit the value size to 1 kilobyte. Let's look at my solution. So here we have the key value database. I'm starting by the main handler function, which is doing routing based on the method. So if the method is post, I'm going to call the post handler, which we'll see in a bit. And if it's a get, we're going to call the get handler. Otherwise, we're going to return an error that the method is not allowed. The router in the standard library is pretty basic. You can use more advanced routers, such as Gorilla MOOCs, if you want fancier routing. So here's the get handler. We're getting the key, we're trimming the leading slash from the path, and then getting the data from the database. If we can't find the data, we return status not found. Otherwise, we write the data outside. When we get a post request, we again trim the leading slash, then defer closing of the request body. We limit the data to a single kilobyte, and we do a read all for the data. If there's an error while reading, we're saying that it was a bad request. And then we set the data and we printf that there was a set. And finally, in the main, we create a server, we route the handle to the main handler, and then start the server. So let's run our code. And now in the terminal, I can do curl http localhost 8080/go, and I'm going to say that the data is rocks. And now we can do curl http localhost 8080/go, which is just get, and we are going to get back that go rocks.